Before we start, let's give a quick remark to Theorem 1.15. So in part C, we talk about that if in X, the topological vector space, there exists a neighborhood that is bounded, then given a sequence that converges to 0, decreases to 0, this family forms a local base. And this is actually the assertion we mentioned in the previous. Let's see which theorem was it. I think it's 1.9. So in theorem 1.9, we mentioned that the part it says that if X is locally bounded, then there exists a countable local base. So that proves the part A of this theorem, which is the main result of this chapter. Okay, so next we're talking about linear mapping between topological vector spaces. So the notation are similar to what we had before, or in calculus, we denote a function like this, which stands for a function from x to y. And if A is a subset of X, then we have the image of A. Denotes like this, and we have a pre-image of B, denoted like this. So this simply means that every X in X such that f of X lies inside B. Though this is just some normal notation that we have here. Now, if X and Y are over the same scalar field, the same phi, either real numbers or complex plane, then we can define the linearity. So a function lambda is said to be linear if for every scalars alpha beta in the scalar field we have and two vectors in X. Then it's linear. And we'll also write lambda of X just as lambda X as it is linear. We'll just omit the parentheses here. And in particular, if the function lambda is from a vector space to the vector field is over, this is called a functional. It's just a fancy name for this special function here. So by linear functional, it means that it is linear and its image is a scalar field. So for example, we have the scalar multiplication operator. This is a linear function or linear operator. However, the translation is not. is not, except for x is 0, which is just an identity. So scalar multiplication is linear, but translation is not. So here are some basic properties that we will not prove as their immediate result as a linearity. So we have lambda 0 is just 0. And if A is a subspace of X or convex subset or balanced set or balanced subset of X, then so is lambda A. And similarly, if B is a, so same deal here. So let's just copy it. It's a subspace or convex set or a balanced set of Y. Then so it's its inverse image of B. And in particular, the inverse image of the 0 subspace of Y is called the null space, and it will be denoted by this. So null space of lambda, which is the same notation as the linear algebra. Now let's give a easy observation on the continuity, which is stated as a theorem 1.17. So if X and Y are topological vector spaces, then as before, we talk about the continuity of a function from X to Y in terms of the neighborhood of X and Y of 0. So that W be a neighborhood of 0 in Y. We need to find if exists for every W. So if it exists B, the neighborhood of 0 in X, such that lambda X is contained in W, lambda V, and it's continuous. Lambda V, then it's continuous. In particular, this is independent of points in X, by which we mean that we only state the continuity of 0 here, but for any point in the X, for any point X in the space X, we can just translate this property. So that W be neighborhood of lambda X, which is in Y, right? Then we can easily check that X plus V will also lies inside. I should write it as W plus X, as literally denotes the same thing as before. So it's uniform in the sense that it does not depend on the X. So other way of stating that is that for the same V and W above, and for X, Y in X, such that X minus Y lies inside the neighborhood V, we will also have lambda y, lambda x minus lambda y lies inside the neighborhood W. And this is easy to see because you can just vector A inside this, right? So these are the same thing. This is by linearity. But so it is uniform in the sense that this choice of neighborhood V does not depend on the point you choose. So the only thing matter is the continuity at 0. Next, we can prove some equivalent properties of continuity. So this is theorem 1.18. And lambda is a linear functional on the topological vector space X. And suppose that there exists X such that lambda X is not identically 0. Then the following are equivalent. So first we have lambda is continuous in the above sense. Second, the null space and of lambda is closed. C, and lambda is not dense. D, there exists a neighborhood of 0 such that is bounded, which is just the same as saying that lambda V is bounded. So the proof is very easy. So A to B says that it's continuous implies that the null space is closed. It's very easy. Lambda is continuous and 0 is closed. And by equivalent definition of continuity, the inverse image of a closed is also closed. It's closed. So this is just by definition. Next, with B to C. If it is closed, then it implies that it is not dense. So this is also very easy. So we just look at the null space. Because it is closed, and there exists X such that lambda X is not 0, which means that X is not in a null space, right? In the null space. This already shows that it is not dense. Otherwise, it will contain all the space. It's not dense. Next, we have, if it is not dense, then there's some neighborhood of X such that it is bounded. So the null space is not dense. Implies that there exists a neighborhood. Let's see how we denote this. So a neighborhood. So let's write it. So some X in X and a neighborhood of 0 such that X plus V intersects the null space. It's empty. Then by theorem 1.14, which states that every neighborhood of a topological vector space contains a balanced neighborhood. So we can just make this neighborhood balanced. So the image of this neighborhood, is also balanced. And it is a subset of the scalar field. But remember we said before that the balanced subsets of are only 3 types. So 0, so it's a interval, disk, or the whole space. So we discussed this before. Because it is non-empty, so this must be bounded, as for this case, or it must be the whole space. If it is the first case, we're done. So let's prove that it's impossible to be the whole space. So if lambda v is equal to the whole scalar field, and we know that lambda x is not 0, then by the surjectivity, by M2 of lambda, there exists y in the space such that lambda y is minus of lambda x, which is equivalent as saying that lambda x plus y is 0, which implies that x plus y is 0, which contradicts the condition over here. So it's a contradiction. Hence, the image of this neighborhood is bounded. And finally, we have D to A. So D says that exists a neighborhood V such that lambda V is bounded. And A says that lambda is continuous. So from this condition, we know that so there exists a neighborhood, let's call it V, such that it is bounded, which in the sense of the scalar field, there exists a scalar element, such that lambda x is smaller than n for every x in the neighborhood. So now, by the definition of the continuity, for any neighborhood of the scalar field, because the balls BR0 forms a local base, is a local base for R larger or equal than 0. So we can just instead, for any R bigger than 0, we find a neighborhood W such that lambda W lies inside this ball R0. And this is very easy. We just let R be R over M times the neighborhood V. So for every x inside this neighborhood. We have that lambda x smaller than m times r over m, which is just r. So this is proven. So this proves that all these conditions are equivalent. And next we'll talk about finite dimensional space.